This video presents a graphical solution to linear programming. Linear programming is a really powerful tool that we use in business all the time, and it takes a look at very simple functions, which are way cool, right? They're all linear functions, but two things are very interesting about linear programming that makes it so useful is, first of all, you can have more than one variable, right? In many applications, actual commercial applications, you have tens or hundreds or thousands of variables that you have to figure out what you want to do with. And then you have all these different constraints. And the constraints are very interesting. For example, you have constraints dealing with your capital, constraints dealing with your technology, constraints dealing with your people. And you'd like to try to figure out how you can best utilize your resources to achieve your goals. And usually your goal is to make as much money as possible, right? And so that's where linear programming becomes very, very powerful. So in this video, we're just going to look at the graphical solution at a very simplistic kind of example. And the example we will look at only has two decision variables that you have to deal with. So the reason for two decision variables instead of 10 or 20 or making it more realistic like that is that we can graph it. And often that graphical, what looks like on the graph, gives you a lot of insight about how this thing works because it does scale up. So the kind of insights you get from just looking at two variables scales up to 1,000 variables. Now, you need to get someone who actually knows what they're doing, like an industrial engineer, in to implement the model with 1,000 variables. But the insights you get from two variables hold. So that's why the graphical solution is so powerful and so useful in learning how this thing works. So this is a very sweet example. I just really enjoy this example quite a bit because it's Half-Baked Bakery, and the bakery just makes two products, cookies and cakes. So it's a diversified baker, but it just makes cookies and cakes, that's all. And so every day they have to come up with their production schedule. Well, how many cookies are we going to make today, and how much cake should we make today, right? And we know something from the marketing people, perhaps, that we make 20 cents for every pound of cookies and 30 cents for every pound of cake. So we're just going to measure everything in terms of pounds. I know that might not be true in practice, but let's just call it pounds because that's simplistic, and I like simple things, if that's all right with you. All right. So first thing I gotta do is, 20 cents for every pound of cookies, 30 cents for every pound of cake. What's our profit function? What's our total contribution for making cookies and cakes for the day? Okay, so let's just call that profit. Might call it net income or something like that. Okay, but sit down and write it out. You say, okay, profit Z is equal to 0.2x plus 0.3y, right? So again, in business, you almost so frequently you have linear functions, right? It's a little bit different if you have to expand your bakery and get another location, and to get more ovens and more people and so on like that, in which case it's no longer linear, but you have a kink, you have a jump in the function. But here, just make more cookies, you make more money, you make more cakes, you make more money. 20 cents for every additional pound of cookies, 30 cents for every additional pound of cake. And there you go, you got your profit function. So just using that profit function, what's the optimal X and the optimal Y? How much should we make every day? And what should we make? Should we make more cookies or more cakes? Probably saying, well, if it's 30 cents for every additional pound of cake, probably we should make more cake than cookies, right? Why not? And how much should we make? Should we make 100 pounds, 1,000 pounds, 1,000,000 pounds? Well, I guess we're going to be headed to the great cookie age, where the whole world is covered in 2 miles of cookies, because the more you make, the more cookies you make, the more profit you make. So the more cake you make, the more profit you make. So the math answer is, infinity, make as much as you can. Well, obviously, no one's going to do that, right? And in this case, our bakery has 3 operations, right? Just to make things simple, not to confuse our graphs very much. It has a mixing operation, a baking operation, and icing operation. So the first thing that the baker does is throw the flour, the sugar, the butter, blah, 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 into a big mixer and mixes it up. And it takes 0.3 hours for every pound of cookie and 0.3 hours for every pound pound of cake and they have a total of 210 hours of capacity for a day, right? And that's how much they can mix up. Same thing for baking. They have the ovens, and each pound of cookie takes a quarter hour. Each pound of cake takes a half an hour, and we have a total of 250 hours of baking or oven time available to us every day. And now icing is a little bit different. Only cakes are being iced, right? So only put icing on the cakes, and each pound of cake, I probably would want to do a number of cakes, right? But 0.2 hours for each pound of cake, and we have 80 icing capacity for a day, right? So you might be thinking there, hey, I thought there's only 24 hours in a day. How can you have these big numbers? Well, yeah, okay. So if you think about mixing, you have the baker there mixing. Well, you could have more than just one baker mixing it up. You could have multiple bakers mixing it up, or you could have multiple mixing machines. You just don't have one oven. You have multiple ovens cooking this, and so on. So you can have more hours of capacity than 24 in a day. Okay. So that's our operations, right? And we have these capacity constraints. So now it's like, well, okay, that's going to limit how much we can make, right? It's going to limit how many pounds of cookies we can make and how many pounds of cake we can make. It also is, hey, these things use up different amounts. Maybe that will tell us what mixture of cookies and cakes we should produce. Okay, so here's how we write down the capacity constraints, right? They're inequalities, and what we have on the left-hand side is just how much we use up. So if you look at baking, right? If you look at the baking, every pound of cookies consumes or eats up a quarter hour of oven time, and every pound of cake consumes a half an hour of oven time, right? And so that's what we're doing here with these linear equations. And we know we have this constraint, right? We have a capacity constraint. It maxes out at 250. We just physically can't run the ovens more than 250 hours in a day. Okay. Same thing for mixing. It tells you how much, if you make X cookies and Y cakes, this tells you how much mixing time you used, and you can only max out to 210. Icing, you have 0 for X, right? We don't ice the cookies, just icing the cake. And so this tells you how much icing time you're using, and you're maxed out at 80. Okay. So one of the things we can get from this, just looking at cookies and cakes, is what can we do and what can't we do, right? What's feasible? If the head baker comes back and says, hey, I'd like to do the following for today, you can say, hey, can we actually make it or not? Okay. And that's called the feasible region. So this is in the cookie and cake space. Got cookies down here on the x-axis and cake up here on the y-axis. This is a nice space I'd like to be in, a very sweet space. And so what we want to do on the space is plot what's feasible. What can we actually do given our production constraints? So what combinations of X and Y can we produce? What combinations of X and Y we can't? And so what we do is just start, plotting. Change those inequalities to equalities and plot those lines, right? Just plot the lines. And again, I'm a kind of a simplistic kind of person. I like to be simple. And one of the simplest way you can plot a line is just to find 2 points and connect it, right? So you find 2 points on the line and connect it, and even make it even simpler. The simplest math I know is with zeros, right? 0 times anything is 0. That's wonderful, brilliant. 0 plus anything is whatever that other thing was. So that's brilliant. That's the kind of math I can handle even in my old age. And so what we do is you set X is equal to 0 and you solve for Y. That gives you 1 point. Then you set Y is equal to 0 and solve for X. It gives you another point. Got 2 points, you connect them, and you're on your way. So we just take the mixing constraint, set X equal to 0, and you say, hey, 0.3 Y is 210. Wonderful. That means Y is 700. So you got your first point. Then you get the second point, set Y is equal to 0 and solve. You find, hey, X is 700. Got the 2 points. You put them down on your graph, blank. Okay, then you get your ruler out and you connect the 2 lines. And there you have it. Okay, 0.3X plus 0.3Y is equal to 210. Now, that's not the constraint, though. That's just equality. The constraint is less than or equal to. And now you have to decide, well, on what side of the line do you want to be on? Right? What side of the line is less than or equal to? And of course, Once you've done this a few times, you get kind of used to it, but until then, you might say, hey, just really don't know. What can I do? Well, what you do is just try a point. Try 0, 0, try the origin, right? Put 0 in for X, 0 in for Y. You say, is 0 less or equal to 210? Yes. So, okay, so that means you're going to have to shade down here. This is what's feasible to do with this mixing constraint. Okay. And so, as another test, you might want to put in 1,000 and 1,000, put 1,000 and 1,000 in this equation. Does it satisfy the inequality? No. So we know that the part on the top here is not feasible. Can't do it. So just with this mixing constraint, you say, okay, there's the area I can produce. So if your head baker came back and said, hey, I'd like you today produce 400 pounds of cookies and 200 pounds of cake, you'd give them a thumb up and say, yes, we can do that. We'll get right on it. Whereas if the head baker came back and says, I'd like you to produce 800 pounds of cookies and 600 pounds of cake because we want to make a lot of money today, you say, yeah, I know what you mean. I like to make a lot of money too, but we have an issue. We just can't do it. We just don't have the capability. Okay. So that's what this is representing, what you can do and what you can't do. Now, of course, you also have a baking constraint, right? And so you can do the same thing with saying X is equal to 0 and solving for Y, you get 500. So 0 and 500. Set Y is equal to 0 and solve for X, you get 0 and 1,000. Connect the line. And again, because it's less than or equal to, you'd be shading this part below it. And that gives you what's feasible for your ovens, right? What can you put in the oven? And then icing is a little bit tricky, right? Because there's no X in it. And so icing is just a constant. You put X is equal to 0. Well, what is Y if X is equal to 0? It's 400. If X is 1,000, what's Y? Well, it's a 400. It's a straight line, and you're in this region below it, right? So cookies doesn't matter because you're just icing cakes. I don't care how many cookies you make. I'm just icing cakes. Go away. Don't bother me with your cookies. Okay. Now, the thing is, to find the feasible region for the entire day production, you need to overlap those three graphs and find the common intersection. So we're going to do some intersectionality here. All right, so here's the intersectionality. We overlap the three graphs and we find out what's in common. And you end up with this lower region, right? This is where all three intersect with each other. It's the lower region. All three constraints need to be satisfied to make it, right? It doesn't matter that you say 600 pounds of cookies and 300 pounds of cake. You say, well, that's okay for this constraint, or 200 pounds of cake, but you're not meeting the mixing constraint. You're meeting the baking and icing, but you're not meeting the mixing. That would not be a valid answer. Okay, so this is telling what you can do. So yeah, you can do 200 and 200. You can do 400 and 300 and so on. You can't do anything up here. So this gives you your feasible region, which is shown in here. The red line around it is called the efficient frontier. That's the frontier of the feasible region. We'll see in a few minutes why it's called the efficient frontier. You want to be along the efficient frontier to do as best as you can, right? You don't want to be on the internal part, if you can help it. Okay, so let's go on. Where's your profit? Well, your profit's not on that graph, right? Your profit is coming up. It's the z-axis. So X is cookies, Y is cake, Z is profit. It sits on top of it for every combination of cookies and cakes. You can figure out how much money you're going to make for the day. Brilliant, just brilliant. 0.2X plus 0.3Y. Okay, and so let's take a quick look at something called the ISO profit line. ISO means same. So let's turn around. Let's say you want to make $100 for the day. Okay, so the CFO comes in and says, hey, we need to make $100 today. You guys get on it. Make how many ever cookies and cakes, but I want to make $100. And you say, well, let's turn it around and find out what combination of cookies and cakes makes $100, right? So you set 100 to Z, you find X and Y. X is 0, then Y is 333. If Y is 0, then X is 500. And you can go ahead and plot that. And that line is actually this thing here. Okay, so, these different color bands, 50 to 100 color band is here, 100 to 150 is here, a profit at 100 is here. And this is just, it looks like it's slanted a little bit from the perspective, but it's just a flat line. Okay, $100. Okay, Now, if you turn it into the cooking cake space, on a contour plot, right? If you've ever gone hiking, you've seen contour plots before, and land elevation plots, and this is where that 100 ISO profit line for 100 is right along here. So all of these combinations of cookies and cakes along this yellow line will produce $100 for me, right? And so I can go ahead and plot that in terms of our feasible region. And you notice that that line is within our feasible region. Hey, that's great. We have lots of flexibility in meeting the CFO's demands, right? We can go here 200 and 200 or 400 and 100 or whatever. And that way we get $100, okay? But, you might say the operations people, the baker would say, well, that's fine, CFO, but we could actually probably make more money. Don't you want to make more money than less money? And, CFOs may not be the brightest light, but they might say, yeah, I want to make more money. And they say, well, let's go ahead and try to make $250. You say, okay, this is the direction of increasing profit, go up to $250. This is the ISO profit line for 250. So everything along this boundary, along this line, will give you a profit of $250. But, there's a fly in the ointment here, right? The thing is, you can't do it. Right? You just don't have the capacity. So where the really sweet spot is, this is showing up here. I went from 100 going up to here to 250, but I blew past the feasible region, right? So by going up, I blew past the feasible region, went beyond the efficient frontier to an area of the unknown where I fall off the edge of the earth. I can't do it. And so where you want to be is just where that ISO profit line just kisses that efficient frontier, right? Or it's tangential, right? The ISO profit line is tangential to the convex hull of the efficient frontier, blah, blah, blah. But, just where you want to kiss, that's where the magic happens. That's where the love is. And so, that's where you'd like to be. You'd like to end up right there. Okay. And so that's where all the magic happens, is at that point. Okay. So where is that point? Well, it's the point that just barely nixed the feasible region, right? You can't go any farther, right? You move this green line. Think of it as, if you had a little crank on it, you could crank it up and down. You just crank it up until you just barely just start to leave. If I crank it any farther up, right? Crank it up because I want to make more money. I can't crank it up. Or if you look at this green line, that's outside the fee. So how can I bring it back in? So just crank it down. Keep the same slope, but just crank it down until eventually it just hits the red. And that's where the magic happens. Okay. Great. So that's where the optimal production is. So we're going to make 400 pounds of cookies, and we're going to make 300 pounds of cake, right? The optimal point just hits that corner point, and our daily profits will be $170. Let me just go back for a second. And so regardless of where your profit function is like, you could change the coefficients a little bit. And if you change the coefficients of your profit function, what happens is these lines start to tilt, right? And so where it's going to hit is always going to be along this upward boundary. Okay, that's the efficient frontier. So even without knowing what your profit function is, just knowing that the more cookies you make, the more profit you get, and the more cake you make, the more profit you get, right? Because it's a linear function. It's a linear function with positive slopes. The more you do, the more you get. I know that my solution is going to be somewhere along this red line, okay? And it's probably either going to be at one of these corner points, okay? It's usually at one of these corner points. Someplace it might be every combination along a line segment. But typically, your optimal solution is going to be at a corner point, okay? And next lecture, we'll see how we can do that, not visually, right? This is kind of hard work doing it visually. We'll be doing it in a much better fashion by using Solver, okay? And Solver is something that comes in Excel. It's an add-on. It's not made by Microsoft. It's made by Frontline Systems. When you first load up Excel, right, if you get a copy of Excel and load it up, it won't be there. it should be under the data tab on the ribbon, but often when you first get Excel, it's not there because you didn't automatically load it up. And the way you load in an add-in is you go to File, at least on the PC versions, right? I'm not an Apple user, I'm sorry to say. I try to buy Apple products, but they turn me away because I'm not cool enough. And so anyway, enough about me. You go to File, Options, Add-ons. I think in Apple products, you go to the Apple symbol, whatever that is, Options, Add-ins. And then you select Excel add-ins, go down to Manage, okay? Then you go, and then you check Solver add-in. Well, we can go through that next time when we actually do Excel. Okay, great. If you like this video, please give me a thumb up. Give me some comments. Let me know how I'm doing. If you'd like to see other kinds of videos like this, just let me know. And I have a lot of other material I can post on the internet here. And so great. Thanks very much. Hope to see you in the next video.